In this video we're going to look at the equation for a circle in its most basic form, when the circle is centered at the origin. Now there are a few reasons why I want to get into circle equations over the next few videos. Firstly, theoretical circles, i.e. circles that exist in theory but not necessarily physically in our CG scene, they're very useful for us to work with. Circles can be a very elegant form for simplistic bounding areas, for example. So sometimes we may have some obscure shape, and it may be more accurate to fit a circle to that shape as a bounding circle and calculate the properties of that circle than it would be to fit a box to that shape and calculate the properties of that box. Also, as we're about to see, the circle equation relates directly to Pythagoras' theorem, and therefore, since we've only just discussed Pythagoras' theorem, I felt it was quite appropriate to discuss circles at this point. In addition, circles are fundamentally important to trigonometry, as we're going to see in the later DVD that focuses on trigonometry. However, one of the main reasons for introducing circle equations is to show that a variety of geometric shapes, so not just lines but other geometric shapes, can be represented as equations, and then to show how these equations can allow us to solve problems that, if we weren't using the equations, would actually be quite hard to solve. So in this case, once we've looked at circle equations and circle theories, we're going to conclude this DVD by intersecting a line with a circle. Now it's very easy to do this when we're working with the equation for the line and the equation for the circle, and hopefully that video that concludes this DVD is going to highlight the flexibility and power of everything that we've covered up until that point in this training DVD. So let's start out. We've got our 2D Cartesian axes, and I want to draw a circle that is centered about the origin. But because I'm not exactly good at drawing on this Wacom tablet right here, I have a pre-made circle that is a perfect circle using the tools in Photoshop to give me this nice, accurate circle. So what do we know about this circle? Well, we know that any point on the circle is going to have coordinates in 2D, so it's going to be a point x, y, and we know that any point on the circle, no matter where on the circle that point lies, it's always going to have the same distance from the center of the circle, and that distance is called the radius. It's a constant value for the entire circle. So we can draw a line from our origin up to our point, and this line, the distance, the length of this line is our radius, which I'm going to label with a capital R. So we know that we have a radius, it's constant for the entire circle, and we also know that a point on the circle has the coordinates x, y. Well, using Pythagoras' theorem, we can relate the radius of a circle to this point, to the coordinates of x, y. So we've seen how we find the distance between 2 points. Well, we're basically doing that now. We're finding the distance between our origin and our point, and we can do that by constructing a right-angled triangle where our radius, the line that goes between those 2 points, is our hypotenuse. So to construct that triangle, we're going to need a line that runs parallel to x. In this case, it's actually going to be our x-axis, and then a line that runs parallel to y. We know because they're parallel to x and y are perpendicular, these two lines are perpendicular, and because one line is only travelling in x and one line is only travelling in y, we can use the x and y coordinates to work out how long those lines are. In this case, the line that's travelling in x goes from 0 up to our x coordinate, therefore it must be x units long, and the line that's travelling in y goes from 0 up to our y coordinate, therefore it must be y units long. So we now can see that we have 3 edges of a right-angled triangle. One is x units long, one is y units long, and one is r, our radius, units long. And using Pythagoras' theorem, we can relate these 3 edges. We know that x squared plus y squared, i.e. these 2 edges, squared and summed, are going to be equal to the hypotenuse squared, to r squared. So x squared plus y squared is equal to r squared. And this is true no matter where on the circle our point is. So if I was to draw some point, I don't know, over here on our other quadrant of the circle, again, let's say this is x2, y2. In actual fact, let's just say this is xy so that we can show that it is indeed the same equation before I try and confuse matters. So xy, we'd have another line That line, because again we know our radius is constant for our circle, is the length r. And if we were to drop another line down parallel to y, a line parallel to x, we can form another right-angled triangle. This distance would still be x, this distance would still be y, and Pythagoras' theorem still holds. So no matter where in the circle we have our point, we always have this relationship of x squared plus y squared is equal to the radius squared. So what we've actually discovered by applying Pythagoras' theorem to some facts that we know about our circle is the circle equation. This little guy is the equation for a circle that is centered about the origin. And that's it. It's a really nice little equation, very easy to derive this equation using Pythagoras, and it's a very easy equation to remember. So given how closely related this equation is to Pythagoras, it's basically Pythagoras' theorem just with slightly different letters being used. I'm not going to give you any examples that I'm personally going to work through. I'm just going to immediately jump to setting you guys a couple of questions. So the first question that I want to set, question 1, is if we have a circle centered at the origin where the radius is equal to 5 units, and a point on the circle has an x-coordinate of 3, what are the 2 possible y-coordinates that this point might have if it lies on the circle? So go ahead and pause the video, give this question an attempt. If you come up with a solution or you get stuck, unpause and I will work through the solution on the whiteboard. Okay, welcome back everyone. So we can see we have our circle equation, x squared plus y squared equals r squared. So x squared plus y squared equals r squared. And we have some of the information here. We have r, we have x, and we're trying to find y. So it's a simple case of rearranging this equation to solve for y. And hopefully we're very, very comfortable doing that at this point. So we can see that y squared is equal to r squared minus x squared. Therefore y is equal to the square root of r squared minus x squared. But notice y is not a distance in this case. Y is a coordinate, and that means because we're not just finding a distance, we must remember it's plus or minus the square root. That's why we can get 2 different y coordinates. And we can see this on our circle. If we had an x coordinate, say, of 3, and let's stipulate for whatever reason that this point here had an x coordinate of 3, there are actually 2 points on our circle that could have an x coordinate of 3. One up here and one down here. Both have a y value, but one is positive and one is negative. So one is going to be the positive square root of this value, the other the negative square root of this value. So there are always 2 points on the circle that will share the same x coordinate, one up here, one down here. Likewise, as I just pointed out, there'd always be 2 points on a circle that would share the same y coordinate. If we had this negative y coordinate, there'd always be another x coordinate that would share the same point on the circle. So when we're solving and we have one of the coordinates of our point, there are always 2 possible solutions for the other coordinate of that point. So y is equal to plus or minus the square root of r was 5, so 5 squared, minus x is 3 squared. That means that y is equal to plus or minus the square root of 25 minus 9, which means that y is equal to plus or minus the square root of 16. Well, the square root of 16 is 4, so y is equal to positive 4 or negative 4. These are the 2 solutions for y, where if we had an x-coordinate of 3 and a radius of 5, y is either equal to plus 4 or minus 4. They're the 2 possible points that would sit on that circle. So there's our first question. And since we're running out of whiteboard space, I'm going to hide all of this, bring up a new layer. And I'm going to set our second and final question for this video. So question 2. Now this question, we know we have a point 10, 6 that lies on a circle, and that circle is centered about the origin. In this case, I'd like you to tell me what the radius of that circle is. So go ahead and pause this video, and once you have a solution, or if you get stuck, unpause and I will work through the answer on the whiteboard. Okay, welcome back everyone. So we're using our circle equation again. X squared plus y squared is equal to r squared. In this case we're simply solving for r, so this is quite a simple equation. We know that r is going to therefore be equal to the square root of x squared plus y squared. We can plug those numbers in. R is equal to the square root of 10 squared plus 6 squared. That's equal to the square root of 100 plus 36, which is equal to the square root of 136. This isn't a nice round number, so I'm going to leave it written in this form, but in case you use the calculator to solve this and you just have an approximate value, the approximate value of root 136 is 11.662. So as long as you got one of these two answers, then that's absolutely fine, or an answer that's close enough to this, since this is an approximate rounded value. So okay, this was a nice simple video in which we derived the equation for a circle centered at the origin using Pythagoras' theorem. Now it's worth noting that this equation doesn't actually make drawing a circle very easy. If we were to hide this guy, bring back all of these, if we were to have a circle and we were trying to draw that circle to our screen, for example, if we were programming the algorithm in order to draw a circle to our window, to our screen, this equation, x squared plus y squared equals r squared, wouldn't be very easy for drawing that circle. We'd have to guess at x coordinates to plug into our equation. So we'd be guessing at different x coordinates in order to calculate the two y coordinates that correspond to that x coordinate. And that's not a good way to draw a circle. We don't want to be guessing at x coordinates to try and get to the y coordinates. Now we're going to see a different equation that is derived from and based on this equation in that later DVD on trigonometry, and that version of this equation is going to be much better suited if you were trying to write a program to draw a circle on the screen. So this is useful for solving problems with circles, but it isn't so useful for drawing a circle to the screen. If you wanted an equation where I say, I've got a circle, it's got an origin at 0 and a radius of some value, and I want to be able to draw that to my screen, this isn't the equation you'd really use. There is another equation that we're going to see in the DVD on trigonometry. So that's the equation of a circle centered at the origin. In the next video we're going to take a look at how we can take this equation and develop this equation to allow us to position the circle at any point. So it doesn't just have to be centered at the origin, it can be positioned anywhere in 2D space. But that is going to conclude this video. Thanks a lot everyone.